Before we begin talking about the velocity triangle of fluid machineries or turbo machineries, let's see one example of turbo machineries. In this term, we will be talking about a pump. So normally, if we look from the front side of a pump, it will look like this. We have the center point where it calls as the eye, and then we will have the outer part of the eye, and it has also blades so now that we know that this is the eye and a set of blades and eye called as the impeller. So it is also often called as the rotating part of pump. And the second part of a pump is the casing. So let's say that the fluids comes in and then it will rotate and live through here. So in this case, the pump receive energies, or they transfer the energy from the pump to the fluid. So pump get the energies to rotate the impeller from an electric motor normally. So if we look on the side view, so the side view of the pump will look like this. That we also have the case of the pump connected to the discharge line. So the fluid comes in and being rotated by the impeller here through the eye and then lifts through the outlet. To perform an analysis of the velocity triangle, we only need to analyze a single blade of the impeller. So this is to make the analysis simpler. On the previous slide, we already discussed about the part of a turbo machinery. So now we know that the impeller has, this is the eye of the impeller, and then actually at the eye of the impeller, we have the inlet. This is the inlet of the fluid, and this is the outlet of the fluid. And the impeller rotates at angular velocity of omega. To make the analysis easier, we will only take this part of the impeller. Now that we have a clearer image or drawings of one single blade, now that in this area is our inlet or area 1, and this is the region of the outlet or area 2. So this is tip, so this is the eye, tip of the eye of the impeller, and this is the tip of the blade. So between these two particular area, so this is inlet and outlet, and the blade has an angular velocity of omega. Now let's say that we have this white dot as the center of the radius, and then we will have R1 as the radius of the inlet, and we have R2 as the radius of the outlet. Now we can begin to talk about the velocity triangle itself. So to make it easier for us to analyze, I will erase this part of radius. And now then we have the first component of the velocity. It's called as the relative velocity of the fluids that comes into the impeller to the inlet. And we normally note it down as velocity is a factor, so it's W with factor symbols on it. So this is called as the relative velocity. So this is the relative velocity between or when the fluid moves with the plate. As we know that the blade is moving at the angular velocity of omega, we also can get the velocity or speed of the blade, or the blade velocity. So as the blades move this way, and the velocity components of the blades, or we can call it as U. So U is the blade velocity. As we know, that is a function of omega multiply with the radius. So at this point we still talk about the inlet sections, and also at the outlet sections we can also have W here. So to distinguish between the inlet and the outlet, we can put here as W2, and this is W1, and we have U1 here. And at the outlet part, we have U2 to that direction. The last component of the velocity triangle, it's called as the absolute velocity. So to close down this triangle, so we will have here as our absolute velocity, or we call it C1 for the inlet, and here we have C2 for the outlet. So C is the absolute velocity. So far we know that there are three velocity components that we need to construct a single velocity triangle. So the first one is factor of W, or the relative velocity, and then the factor of U, which is the blade velocity, and the other one is C as the absolute velocity. If we analyze the triangle itself, we will come with two different type of angles. So the first one is called as alpha. So alpha is the absolute angle, and it is between the blade velocity and the absolute velocity. The other one is beta here. Beta is the relative angle. This beta, or relative flow angle, can also be called as the blade angle. As from these two angles, we can have two new or sub-components of the velocity. In these terms is the absolute velocity from the absolute velocity. So now we can have the radial component of the absolute velocity and the tangential components of the absolute velocity. So which is this is as Cx, and this perpendicular line as the CR, where from alpha we can get the value of CR is equal to C sinus of alpha, and Cx is C cosinus of alpha. So these rules are also applied for the outlet part. So now we only talk about the inlet part of the blade, but for the outlet part the approach will be similar, so you can start to develop the velocity triangle for the outlet part of this drawing. So previously we also know that the power that being generated by a turbo machineries as W is equal as sigma of the torque multiplied with omega, that is equal to mass flow rate multiplied with omega r radius 2 multiplied with cx2 minus omega r1 cx1, and this can be written as, we know that omega r is u, and it can be written as u2 cx2 minus u1 cx1. The omega itself is a function of 2p per 60 multiplied with n, which is the rotation per minute of the impeller. And then for u1 or u2, let's say for u1, we can write it down as omega multiplied with r1, and we can write it down as 2p r1 multiplied with n divided by 60, or 2 times radius equal to diameter, so we can write it down as p d1 rpm of the blade divided by 60. And this is also applied for the outlet, so u2 is equal to p d2 rotation of the blade divided by 60. So far we already know that the power being generated from energy exchange between fluids and rotor is equal to the mass flow rate, or m dot, multiplied with the difference between the product of relative velocity with the tangential components of the absolute velocity at the outlet minus the conditions at the inlet. And in a turbo machinery systems, we also know that power is also equal to the density, the volume flow rate, gravity, and head. Or we can rearrange this second equation into the head form, that now we have head is equal to power divided by density, Q, and gravity. As for the first equations, we know that m dot is equal to density multiplied with the volume flow rate. So m dot is equal to rho and Q. So now let's try to perform some work on the first equation. So we can write down as rho Q multiplied by u2 cx2 minus u1 cx1, and then we can combine this with this equation. So the head of a turbo machinery can be written as rho Q multiplied with u2 cx2 minus u1 cx1 divided by the rho Q and gravity, and we can cancel these two. So the final form of the head is u2 cx2 minus u1 cx1 divided by gravity.